Hello everyone, this is the midterm project proposal presentation for the course ECE 544 Silicon Photonics for Computing Systems. The title of the project is Optical Switches, Ring Resonator Switch in comparison with MZI based switch. My name is Goutham Reddy and I'll be presenting this project. Now coming to the introduction, the demand for optical switching has increased a lot in recent years because of the increase of optical interconnects in high-performance telecommunication networks and modern data centers. State-of-the-art electronic switching techniques have bottlenecks such as scalability, bandwidth, switching speed, data rates, and power consumption. To overcome all these bottlenecks, optical switches looks to be one of the promising component for the next generation optical networks. Coming to the reason why I chose this project is one of the basic operation in most of the modern systems is switching. All the logic operations, data transfer, and major tasks require switching. Today's technology have few limitations to increase the switching speed. So the project aims on different optical switching techniques and the properties of optical switches. In this project, we will start with the basics of optical switches, like what are optical switches and how they work. For demonstration, we choose two types of optical switches, ring resonator based switch and MZI based switch. Later, the pros and cons of each type of switch will be discussed. Now, what are optical switches? Optical switch is a device that is used to open or close an optical circuit. An optical switch can also be defined as a device that selectively switches optical signals from one channel to another. The switching can be temporal or spatial. According to the different fabrication process and its application, there are different types of optical switches. An optical switch may operate by mechanical means, such as physically shifting an optical fiber to drive one or more alternative fibers, or by electro-optic effects, magneto-optic effects, or other methods. The functionality of any switch can be described in terms of the connection it can establish between two ports. A connection is said to be in the on state if an optical signal applied on one port emerges at the other port with essentially zero loss in optical energy. A connection is said to be in the off state if essentially zero optical energy emerges at the other port. Before we dive deep into the project, I have done some research on the topic to get more knowledge. So here are a few papers about optical switches I went through, and here is a short summary of these papers. In the first paper, I read about a silicon scalable multimode switch demonstrated using multimode interference couplers and thermo-optic phase shifters. Multimode switches are also used for switching payload data and are a key component in mode division multiplexing. The device, its design and working principle of these switches is also explained in the paper. The scalable multimode switches can also be used for higher link capacity and better energy per unit performance. In the next paper, I read about the multimode interferometer based thermal optical switches. Other than the cost, these switches have low crosstalk, low power consumption, low loss, and high bandwidth. This is achieved because the design of the switches use wavelength division multiplexing, electron beam lithography, and reactive ion etching. The authors also demonstrated the switches with power penalty dependency on the routing paths with low on-chip loss and low crosstalk. In another paper, I found out the technology that can boost the input-output bandwidth for switching applications is a single-mode silicon photonic switching technology. So, the authors of the paper have designed an electro-optic switch based on PN junction. This design is unique because the real and imaginary part of refractive index changes with the concentration of free carriers of silicon. In a 2x2 switch design, they have shown that switching is highly efficient between 0.7 volts and minus 0.8 volts. In the next one, I learned that Mach-Zehnder interferometer, which are used as switching elements, can achieve nanosecond switching speed, which is great when compared to the electrical switching. But the elements that cause crosstalk in MZI are electroabsorption, loss coupler variation, and phase error. So, to improve crosstalk limit, an advanced control method is introduced that coordinates thermal optical and electro-optical phase shifters. This method not only improves crosstalk levels but also crosstalk susceptibility. Reduction of crosstalk in different switching elements leads to less power consumption. The figure in the slide represents the power difference between output signal and output crosstalk as the electro-optic voltages are varied for a MZI switching element under testing. To build a large-scale switch matrix, optical switch element with low insertion loss, low crosstalk, and low power consumption are highly required. There are two possible solutions for this. The first one is using a third-order coupled ring resonator with tuned middle ring resonator, and the second one is using a second-order coupled ring resonator with tuning applied to bus waveguides. Both of these ideas can build a large-scale optical switch, but with the first one, we can get low on-chip insertion loss and low crosstalk, and with the second solution, we can achieve high optical bandwidth. Coming to the next paper, to design low-power optical switch, MZI and two ring resonators in the MZI arms are used. The relative phase change between the MZI arms causes the switch operation. By using phase enhancement in the mirroring resonator, the power consumption is reduced compared to electrical switching techniques. By choosing appropriate micro-ring radii, the power consumption of the optical switch is almost independent of the propagation loss in the racetrack resonator. Next, to design optical switches for high-speed data transfer, high-quality factor ring resonators are used. These ring resonators are reliable for high-speed modulation and high integration due to their small form factor. Low optical losses inside the cavity and low drive voltages are possible by using carrier injection mirroring resonator. With this method, effective switching for the signal at high speeds can be achieved with low drive voltage. Next paper is an analysis of crosstalk in optical switches. The authors conducted few experiments and found the following results. The MEMS-based switches have around 50 dB crosstalk with high drive voltage and low speed switching time. The MZI-based switches have around 25 dB crosstalk and 5 mW power consumption during high-speed data transfer. Ring resonator-based switches have low crosstalk and low power consumption because of their small form factor. To design large-scale N-cross-N optical switch matrix, different architectural topologies like crossbar, Venice switch can be used. To improve switching extinction ratio in large-scale switches, 3 directly coupled ring resonators with actuated central ring can be used, or rings side couple with the MZI can be used. Both these techniques have passbands which have sharp edges, and they improve the switching extinction ratio. High-speed optical switching can be achieved in these techniques by tuning the external coupler. The image in this slide is a schematic of an MZI based switch. The objective of this project is to understand basics of optical switches with its functionality, applications, and characteristics. Then learn about different types of optical switches. Our focus will be on ring resonator based optical switch and Mach Zehnder interferometer based optical switch. A detailed study on the two types of switches will be made, and we will compare the characteristics like optical loss, crosstalk, bandwidth dependency, wavelength dependency, power consumption, and energy efficiency. We will also discuss the pros and cons of both of these switches. The figure on the right is a computer simulated ring resonator depicting continuous wave input at resonance. Coming to the methodology, after gaining the required knowledge, we will design and implement ring resonator based optical switch and Mach Zehnder interferometer based optical switch in the numerical software. In the design part, our main focus will be to find out the proper materials used and their appropriate dimensions for accurate results. By running different simulations on these switches, the differences, similarities between these two types of optical switches can be analyzed. We will also discuss the characteristics of each switch and explain it in detail. To conclude this, the project aims at understanding optical switches and pick two types of switches, that is, ring resonator based switch and MZI based switch. We will design the switches and run simulations to analyze different properties of the switches. This project will also help us to understand why next generation systems should implement silicon photonics as their future technology. Thank you. The references for the papers mentioned in the presentation are given in the description below.